as Marcel said, I previously did my PhD with Dorsey. So basically, I have already, this is my second time to give a seminar to the SOFLUX. Last time I gave that together with my PhD supervisor, Dorsey. And several years later, I become a little bit more independent. So now I can give a seminar myself. So here you can see the title of my talk today. So a little bit different with what I gave to Marcel several months ago. The basic topic is similar. So it's basically about this temperature gradients impacting the air CO2 flux. But the Southern Ocean observations give more. Is the key of the story of my talk. So now I'm a postdoc at GEOMAR and Heidelberg University. I'm working on the air sea gas exchange and the quantification of the ocean carbon sink. So today I'm going to introduce my one of my key work in the last several years about this upper ocean temperature gradients. So first I will talk about in theory why we should care about these temperature gradients, and then there are some evidence of these two temperature gradients. One is the Coulson effect, another one is this shipboard SST bias issue. And then I will talk about the potential impact based on what we know on the global air CO2 flux estimates. And the next section will be the most important one, is some observational evidence we got recently. And in the end, I will say there's still some problems remain. We can work on them in the future. So first, let's look at the theoretical arguments. So I think everyone is pretty familiar with this bulk equation for the air CO2 flux calculation. So the K is the gas transfer velocity, Cw is the wall side CO2 concentration, H is the solubility, Ca is the air side CO2 concentration. And it's very important to know that all the parameters in this bulk equation are temperature dependent. So the bulk flux, CO2 flux estimate is very, very sensitive to the temperature currency. So below I show the schematic of how the air sea gas change occurs and what kind of temperature we should use for all the parameters in the bulk equation. So here, this black line represents the air sea interface. Above that is atmosphere, and below that is the seawater. And here is a very thin layer called mass boundary layer, and this layer is only 10 to 100 micrometers. This is basically the layer related to air sea gas exchange. And below that is a boxy water, and we assume the seawater can mix in very quickly, so there are no gradients in the boxy water. So in theory, we should measure this part, the air side part, the solubility and the air concentration on top of this mass boundary layer, and measure the Cw at the base of the mass boundary layer. And basically, the temperature should also be measured as corresponding locations. However, this is not possible because this layer is so thin. We cannot do that in the real field measurements to measure that at this thin layer. So in practical, we do the temperature and the Cw measurements at the boxy water at about 5-meter depth, and assume there are no gradients in the boxy water, and the temperature can be used for both the Cw, H, and Ca calculation. However, this assumption maybe have problems. So as we all know, there's a skin layer on top of the surface. So because the surface ocean is generally lose heat from the ocean to the atmosphere, so that generates a temperature gradient in this thermal boundary layer. This thermal boundary layer is about 1 millimeter, so it's thicker than this mass boundary layer. So basically, from the surface to about 1 millimeter, there is a temperature gradient. So the temperature at 5 meters should be different from the from the temperature as a mass boundary layer. So this is the first problem. And the second one is that the temperature measurements is generally observed by the ocean, by the ship. So what we do is that we take the water from the ocean to the body of the ship, and the temperature sensor is often located at the engine room. So if you were on a cruise, you might feel that the temperature in the engine room is higher than the surrounding atmosphere. So this warmer environment may heat the temperature, the intake seawater, and make a temperature measurements have some bias. So do we have some evidence of this cool skin effect and this potential warm bias of the ship measurements? Yes, we have. So this slide shows some evidence of the cool skin effect. So date back to 1996, the FERA created the core model, and this model simulates the cool skin effect and showing the results as these two figures. So on the up figure shows the cool skin effect versus the wind speed, and the daytime and the nighttime, the cool skin effect is a little bit different. And on average, the cool skin effect is about on order of 0.2. And the bottom figure shows that the change of the heat flux versus the wind speed. So basically, the cool skin effect is a function of the wind speed, of the long wave radiation, and the heat flux. So this is just based on the theory and the model. And the right figure shows the evidence from the field. We did measure the cool skin effect from the field. So this figure shows the cool skin effect. Basically, is the skin temperature minus the bulk temperature versus the wind speed. So we can say their difference is always negative. So this means the surface is always cooler than the boxy water. And this paper suggests that when the wind speed is higher than 6 meters every second, on average, the cool skin effect is about 0.17 K for both day and night time. But you can see the cool skin effect is not consistent. It changes with the wind speed, it changes with the long wave radiation and the heat flux. And also we have some evidence of the shipboard SST bias. So this figure shows like the all SST measurements by the ship in this ICO ADAS dataset, and most of this temperature measurements come from the volunteer observing ships. So here, this figure shows the friction of the temperature measurements from different measure types. So this blue area represents the temperature measured by the engine room intake. So basically, in recent years, you can see this type of temperature measurements dominate all the ship SST measurements. However, for this kind of measurements, the research suggests that the temperature are often biased warm due to the heating of the water sample by the ship as it passes through the pipes and even pumps on its way to the engine room. And some assessments suggest that the warm bias could be 0.13 to 0.15 K. But this result is on all the ship-based SST datasets. But for the carbon flux, we use the SOCAD data, and but most of a large fraction of the PCO2 and SST data in the SOCAD also come from the volunteer observing ships. So probably they also have some warm bias similar with this SST dataset in our SOCAD dataset. But there's some difference because the SOCAD data, many of the data were observed by the research ships. And for the research ships, we would expect the SST measured by the ship could be better than the volunteer ships because the scientists often validate the SST versus the CTD measurements. We think maybe there's some bias in the so-called SST, but probably different with this overall SST data set. So the next section is that now we are sure that the Cook-Skin effect is there and the potential warm bias also exists. But how that impacts the ARC CO2 flux is another question. So there's a pretty old research by Robertson and Andy Watson and published a paper on Nature in 1996. And they look at this like the Cook-Skin effect, and they assess like the Cook-Skin effect of 0.3 degree and show that this Cook-Skin effect will increase the ocean uptake of about 0.7 gigaton carbon every year. This is about like half of the annual mean global air CO2 flux. So it's very significant. But with the time increase, we have some new evidence of this Cook-Skin effect and the warm bias issue. So in 2020, the Watson et al. Published another paper on niche communication, and they assume the Cook-Skin effect is about 0.717 K adopt from this Dolan paper, and this will increase the ocean CO2 uptake by 0.4 per gram carbon every year. And then they assess the so-called SST bias using this like satellite SST product, and find like this potential bias in the so-called SST will also after correction will also increase the ocean CO2 uptake by 0.4 per gram carbon every year. So basically, after considering these two temperature effects, the global ocean CO2 flux will be increased by about 0.9 per gram carbon every year. So this is very, very big correction. After that, I did another work and do some revisit of these two temperature effects based on the recent new research. So the first thing is like in this Watson et al. Paper, they use a consistent Cook-Skin effect. But based on the slides I have already shown, the Cook-Skin effect is not consistent. It changes with wind speed, long wave radiation, and heat flux. So I use this FAIRA model to do the assessment, and also a recent study suggests that the core model can pretty well reproduce the variation of the Cook-Skin effect. Another point about this potential warm bias in the so-called SST, I use a drifting buoy as a reference to the assessment. The previous research using this satellite data, but the research suggests that the satellite SST product may have a cold bias on global average. So probably it's not the best to be used as a reference. But the drifting buoy SST measurements does not have this engine room warming process, so should have better accuracy than the ship measurements. So after reassessment of these two temperature effects, I recalculate the global air CO2 flux, and compare that with the previous correction. So on top of this line, represent the global air CO2 flux without any corrections, without any temperature corrections. In the middle, the red one is the correction based on my assessment, and the blue one is the Watson et al. 2020 correction. So my correction increase the air CO2 flux increased by 0.6 petagram carbon every year, and this Watson et al. 2020 calculation increased the air CO2 flux by 15%. So you can see globally these two temperature corrections is very significant, have very significant impact on the air CO2 flux. This is because globally the direct PCO2 is only about -10 micro ATM, and the Cook-Skin effect the impact on the CO2 flux is about 2 micro-atm decrease in the dirt PCO2. So this is why it's significant. But originally, this effect is pretty small. Because if you do the PCO2 measurements, you will find like the dirt PCO2 in many regions is like this huge, is much larger than 10 micro-atm. So if you use the 2 micro-atm divided by the dirt PCO2 you measured regionally, it's a pretty small number. So this is why it's very difficult to verify this temperature effect on the ARC CO2 flux calculation. So, I mean, it's really hard to detect this 2 micro-atm impact regionally. But we did manage to get some evidence. So firstly, here is a research by the Yuanxu Dong. They published a paper on Science in 2021. They also, I yesterday searched the SOFLUX website. I found like he also gave a seminar in 2022. And on top of this figure shows their results. So basically, they do the airside CO2 concentration measurements by the aircraft. So this aircraft measurements is not affected by the waterside temperature effects, so should be free from the temperature impact. So the black bar represents the Southern Ocean CO2 flux by their aircraft concentration, and this blue bar here represents the SoCal-based CO2 flux estimate, and this brown bar represents this SOCOM, this float data-based flux estimate. So basically, they conclude that the aircraft measurements support the SoCal-based flux estimate instead of the float-based flux estimate. But if we look at the black bar and the blue bar, you can see this aircraft constraint is still moderately higher than the SoCal-based flux estimate. But I would like to see this SoCal-based flux estimate does not consider the temperature corrections. And after this webinars, it's like Dorothy and I give another webinar to the SOFLUX. During that webinar, I show some data like direct flux measurements in the Southern Ocean. But during that time, it's just the preliminary results. I didn't give any conclusions based on during that time. And then several years later, we published a paper using the eddy covariance measurements to show that the temperature correction maybe should be included. So what is eddy covariance? So the eddy covariance direct flux measurements. So basically, there are lots of eddies in the atmosphere in the ARC interface. So these eddies are carried by the wind. So there are some small eddies and large eddies, and these eddies reflect the fluctuation of the CO2 concentration in the air, and the fluctuation is because of the flux, because of the ocean uptake and outgassing of the CO2. So if we correlate the vertical wind velocity fluctuation and the CO2 concentration fluctuation, and we can get the CO2 flux. So this method is basically based on the definition of the turbulent flux. So this represents the direct flux measurements. It's not influenced by these temperature effects. So we managed to use the two UK research vessels to measure the direct flux in the Southern Ocean during 7 cruises. And we use this data to compare with the bulk flux estimates, and we got these results. So in this figure shows the CO2 flux estimate or measured by different methods. So in the left, it represents the mean CO2 flux in the entire Southern Ocean. The blue bar is the SoCal flux plus the temperature corrections. And then the second bar is the original SoCal flux without temperature corrections. And then is the SoCal plus this float measurements. based flux estimates, and then it's a float data based flux estimates, and the last one, the green one is the global ocean biogeochemical models. So you can see in the Southern Ocean, basically the flux is not very well estimated. This independent flux estimates have huge difference. In the right side, it shows a comparison of our eddy covariance measurements together with the subsampled flux from these different flux products. So the the black bar represents eddy covariant flux, and then it looks like it agrees best with the so-called base flux plus the temperature corrections. So this provides some evidence that maybe this temperature correction should be considered in the CO2 flux estimate. And also, we find another evidence. So this figure also shows annual mean CO2 flux. So the first bar is still the so-called flux with the temperature corrections. The second bar is this Long et al. 2021 science paper, the aircraft constraint of the South Ocean CO2 flux. And the third bar is the original so-called flux. So it looks like after correct for the temperature effects, the so-called flux agree with this aircraft constraint, but of course this aircraft constraint has a pretty large uncertainty. But at least this shows that they agree better after correct for these temperature effects. And in 2024, there's another evidence by Daniel Ford from Jimmy Shooter's group. They published a paper on Nature Geoscience. They also use the eddy covariance ARC CO2 flux measurements compare with the bulk flux. The results shows in the right figure. So basically, they compare the direct flux by eddy covariance with the bulk flux estimates point by point. And their conclusion is that after consider the temperature gradients, the bulk flux agrees better with the direct flux measurements by eddy covariance. So after we have all these two recent field evidence, the Global Climate Boundary Committee starts to have positive attitudes to these temperature corrections. I still remember several years ago when this Watson et al. Paper published, the committee I feel like it's pretty conservative towards these temperature corrections, but now we have more evidence and people start to be positive. And during the Global Climate Boundary Ocean workshop, we start to talk about maybe we should consider include this correction in the future global climate boundary flux estimate. However, there are still several problems. So first, for example, this study shown here, they only have like 148 points for the comparison, and the p-value is 0.7. So basically, it's insignificant. So and the paper stated that significance is reached with continuous measurements for about 500 days. So that means we need more data to have stronger evidence to confirm this temperature impact. Another question is that if the way we confirm the way we provide field evidence is by compare the bulk flux with eddy covariant flux. However, I mean for this bulk flux calculation, it's not only the problem with this temperature effect. It also includes the gas transfer velocity. I mean, are we really confident with the gas transfer velocity we used for this comparison? So, I mean, we say they have disagreement. Is that because of the temperature problem, or is because of the K has larger uncertainty? I mean, this is to me is the problem. So, for example, in the right figure shows the recent observations of the gas transfer velocity versus the wind speed. So this dashed line represents the Van Hoff gas transfer velocity parameterization. This is the one we often used. And the right line represents the feet based on the eddy covariance measurements in different oceans. So you can see on average, these two lines does not agree perfectly. And another point is that these circles represent the average of the key measurements in different ocean regions. Basically, you can see the error bar is still pretty large, especially on the high wind speed. So this means the K still have pretty large uncertainty. And from the Weininghoff paper, they gave he gave the uncertainty of the K is about 20%. So I mean, this is still pretty large number because the cool skin effect results in about 10% flux difference if the delta PCO2 is about 20 micro ATM. But if the delta PCO2 is 14, the impact will be just 5%. So this small impact probably will be emerged in this 20% uncertainty of the K. So I think in the future, a better understanding of the K is essential to solve these temperature effects. Another problem is that should we use a replied model or equilibrium model? I'm not going to introduce these two models very detailedly. If you are interested in that, you please refer to this David Wolf's paper in 2016. So briefly, so this is like the traditional treatment of the temperature for the flux calculation. Use the Bock equation. We use the Boxy water for all the parameters used in this Bock equation. And now the committee do is like they assume the replied model and only correct for the temperature for this airside parameters, for example, the solubility and the airside concentration. But for the equilibrium model, we should also correct the waterside concentration, not only the airside. And for the equilibrium model, the impact will be about 3.5 micro ATM. It's higher than the replied model. So which one should be used? Which one is the right one? We're still not sure, but just in theory, maybe the replied model is better. But we still need some observational evidence to confirm this. Okay. Another problem is that after consider these temperature corrections, the data products, the so-called base data products, will be even more different with the global ocean biogeochemical models in the ocean CO2 flux. So this figure shows global current budget 2025. This blue line represents the data products, and this purple line represents the models. So you can see they are different. And on average, the difference is about 0.4 per gram carbon every year. After apply for the temperature corrections to both the data products and the models, and this difference is like increased to 0.8. So what's the reason for that? How to explain this difference will be another problem. So why like apply for the temperature correction increase their difference? This is because for the model first don't have this Shieldbolt SST bias problem because the model does not use the Shieldbolt SST data. The second thing is like the cool skin correction in the model is smaller than for the data products because the model the theory of the model to calculate the flux is a bit different with what we use the so-called data. So basically the model have this vertical transport process. So after consider the cool skin effect, there will be more CO2 in the surface, but the transport is pretty slow. So there will be more CO2 accumulated in the surface. So that will damp this cool skin effect. So basically in the model, the cool skin correction is smaller than directly applied to this data product. Okay, so now the last slide, the take-home message. So theoretically, it's clear that the cool skin and the ship SST bias should be considered in the ARC CO2 flux estimates and this impact is pretty large, 0.6 to 0.9 per gram coming every year. And now we have some observational evidence by using the eddy covariance technique, but there are still lots of problems remain. It's good to say like the committee starts to be positive for the correction now, but we still need to spend some effort to provide more, to have more field measurements, and also focus on solve this if the required model, the equilibrium model should be used, and have a better understanding of the gas transfer velocity. Okay, for my Southern Ocean paper, I just what I show here is just part of the story. I mean, if you are interested in that, please look at the paper directly. There are also some discussions in there about this subsample issue, because there are some discussion in the Southern Ocean that we should have high frequency observations instead of like the weekly measurements to capture these small scale processes. So in the paper, we also have lots of discussion on that. If you have any questions, please just ask me. Thank you.
Great, thank you. Thanks very much, Yuanxu. That was great. Carlos has his hand up. If you want to ask a question, either raise your hand or you can ask in the chat as well. I'll monitor that.
Hi, that was a great talk. Thank you very much. I learned a huge amount. You had a slide early on, the number 3, impact on global air-sea CO2 flux, and you're comparing your estimates from 2022 with the Watson results. I don't know if you can pull up that slide.
Yeah, wait a moment.
Yeah.
This one, right?
Yeah, so I was just curious, to my eye, it looks like the disagreement between your estimates and Watson's are larger, kind of before maybe 1995 than after in the kind of the second half of time series. Can you comment on that, that change?
Yeah, that's a good point. So the first thing is that in this like the Watson et al. Paper, they use a constant Coulson effect, but the Coulson effect is not consistent. There's some increase of the Coulson impact on the CO2 flux estimate. This is one thing, but maybe this is not the primary reason. Another reason is that we use very different the warm bias correction. So in the Watson paper, they use the satellite data to do the correction. But from what I do is like I use this drifting buoy data as a reference to the correction. So basically, this bias is a little bit different in different years between these two studies. I think this is the main reason.
Okay, thank you very much.
Thank you.
Great talk.
Do we have any other questions? Okay, I can go ahead. I've got some. I think it's in one of the following slides where you show the differences in the Southern Ocean flux between the different sort of techniques that are used to determine the flux. It's the slide after this. I was just kind of curious, you know, the Coulson correction does bring it close to the eddy covariance measurements, even with the sort of cruise specific observations. But there is still some considerable disagreement there. What do we need to do to still get closer to the eddy covariance? And sort of an adjoining question to that is, how do we take the eddy covariance observations as the dead truth, or is there uncertainty in those as well?
Yeah, that's a very good question, Marcel. I mean, this is also a very big question. I probably can't answer everything, but just just say what I understand.
Yeah.
So for the eddy covariance itself, it's in theory should be the reference because it's the definition of the eddy covariance is the same with the definition of the flux. So this is the most direct flux measurement. But of course, it has pretty large uncertainty in this eddy covariance measurements. But what I understand is that the most uncertainty in the eddy covariance measurements is a random uncertainty. It's not like the systematic bias. It's a random uncertainty. So that means if you have lots of measurements, you average them. So basically, we would expect the random uncertainty should be mostly reduced, should be minimal.
Mhm.
But of course, we had like a workshop last year in London of this eddy covariance ocean committee. We found like from different groups, even the data processing will generate some difference for the eddy covariance data. So basically now I think we are still making lots of effort to make the standardization of the setup of the data processing. There will be a paper come out, I guess, in the next several months or maybe next year, to about this workshop to say about this standardization of the data processing and setup. But I mean, right now, I think I personally think that the covariance. I mean, my understanding is that this is probably the most direct way we can find the evidence to prove this flux, right? I don't know, but maybe I also think about that because this is also very difficult to do in the field. But maybe we can do that in some way in the laboratory. So in the laboratory, like in the wave tank, we can do the mass balance measurements. The mass balance is also like pretty reliable, and we like correct a higher more significant cool skin in the surface by, for example, below a cold wind on the surface to create a pretty large cool skin to make the effort more significant and confirm this question. But I didn't see any people working on that. But maybe there could be a try in the future. But I mean, like what you said about this Southern Ocean flux, even after we consider this temperature correction, of course, there are still lots of disagreement between different observations. But I mean, this is like a pretty difficult question to answer. But I mean, I think the basic question is that the basic problem is that in the Southern Ocean, we have a few data. We don't have data in there. And also Southern Ocean is so dynamic, it's so variable. I mean, we need more data, but we have few data in there. And also, if you look at the model in the Southern Ocean, the seasonality from different model is hugely different. Some model even simulates the sink. Some models simulate the source. So it's like the sink or source difference. So I think we still need to have lots of time to go in the Southern Ocean CO2 flux estimate. This is just my personal thoughts.
Thank you. That makes sense. Tiago.
Hello, is everybody hear me?
Yeah.
Okay, so thank you very much, Dong, for your great talk. And well, I was wondering if you have seen or you look at some dependence of the amplitude of the sea surface temperature or any influence of the temperature on the cool skin effect on the CO2 flux.
Thiago, thank you for your questions. Thank you for coming and long time no see. But I did actually get your point. Could you repeat again?
Yeah, I was wondering if you have seen any influence of the amplitude of the sea surface temperature, the change in temperature if the temperature have an influence of the cool skin effect on the CO2
Ah,
flux. You know,
okay.
I know that you mentioned about the influence of the wind speed, for example,
Uh-huh. Yeah.
but I was wondering if the temperature itself have any influence in this impact of the cool skin.
Okay, thank you. I get the point. So I mean, the temperature itself is not the reason to change the cool skin effect. If you look at this figure, I think you still can see my screen, right?
Yes.
So basically, so this figure shows like the cool skin effect versus the wind speed. It changes with the wind speed, and you can see the daytime and nighttime they have difference. This difference is because of long wave solar radiation is different in the daytime and nighttime, and also the heat flux is different. It's not because of the temperature itself; it's the temperature difference determines the heat flux, and also determines the long wave radiation. That really matters. It's like what makes the the heat loss more significant really matters for the cool skin effect is
Yeah. Oh.
instead of
Yeah.
the temperature
Yeah.
itself.
Yeah, I got it. And another question that I was wondering is when you compare the fluxes in the Southern Ocean, for example,
Mhm.
between the eddy covariance method and the book method, did you observe or you see any did you look at the comparison of the PCO2, for example, resulted from the eddy covariance
Mhm.
with the PCO2 from the SOCAT
Mhm.
measurement. Did you see that?
You mean like compare the PCO2 in SOCAT with the eddy covariance data?
Yes, because I was wondering, for example, when you measure the CO2 flux by eddy covariance,
Mhm.
we can use the PCO2 in the
Mhm.
atmosphere
Mhm.
and then calculate the PCO2 at the sea surface, right?
Aha. Okay. Yeah.
So if we compare
Mhm.
the PCO2 resulted from this,
Okay. Yeah.
the culprit with the PCO2 measurement
Uh-huh.
directly in the
Okay.
SOCAT,
Yeah.
did you see there is,
Okay. Yeah.
very
I
great
get the point.
correlation between them? Yeah.
Yes. So this is basically, I think, the same question. So here we compare the flux. We compare the eddy covariant flux with the bulk flux. The bulk flux is calculated by the direct PCO2 from the SOCAT data or from our direct PCO2 measurements. But I mean, you mean like I can back calculate the PCO2 in the air or in the water and compare that PCO2 with the SOCAT PCO2, right? With the
Yes.
PCO2 measurement. I mean, it's the same question. But I think this kind of calculation is not ideal. I did some work previously in Arctic Ocean for another paper, but for this case, maybe this is not the best way to do because I can show you why it is. Um, so if you look at this paper, so what you mean is like we use the eddy covariance flux and divide the K and plus the HCA to get the CW, right?
Ye-
So this way you need to divide the K. So as I said, the K has pretty large uncertainty. If you divide like a value with pretty large uncertainty, especially when the K is small, there will be huge uncertainty propagate to the results. So you will see like your back calculated CW using this method is very sketchy. It's pretty sketchy. So
Yeah.
I don't think we can based on that to get any conclusion on the comparison. But if the direct PCO2 is huge, I mean if the signal is very large, or if the wind speed is high, the value of the K is larger, maybe this is okay, but not at low wind speed or when the signal is small. The uncertainty will make the comparison very difficult.
Yeah, I got it. So thank you very much, Don.
Thank you.
Hope to see you soon.
Yeah.
We have a question in the chat, Yuanxu.
Mhm.
The question is, what methodology did you use to correct wind data due to ship motion? That's from Selena.
Okay. That's a good question. About eddy covariance, and I'm very happy that some people interested in the method. And Marcel also know that we did some work together to do the motion correction. So here I give some instruments for what we used to correct for the wind for the ship motion. So basically, we use sonic anemometer to measure the vertical wind velocity. And we also, at the same time, use a motion sensor attached to the sonic anemometer to sense the movement of the ship, and use this signal to do the correction for the vertical wind speed. And this method, um, like before 2000, we still cannot do it very well, but the Edison paper generally prove that he give a method to do the correction, and prove that the correction is pretty sound. And this is also very good progress why we can use the shield-based eddy covariance system to measure the CO2 flux. So yeah, we can do that. We use the motion sensor to sense the ship's motion.
Thanks. Do we have any other questions? I'll kind of leave you with a little bit of a tricky one. So, there is obviously still some uncertainty around the flux estimates that we obtain from taking ocean observations of bulk parameters. That's due to both the K term as well as us not being able to represent the ocean fine scale and its variability very well. Where do you think we should go in terms of our efforts to try and improve our understanding of carbon fluxes, CO2 fluxes? Is it more efforts towards the K, refining the K parameters, particularly at low and high wind speeds, or is it trying to target certain areas around the Southern Ocean and globally to understand more of the fluxes there?
I think, yeah, this is definitely a tricky question and also a big question. I mean, as we have discussed, like in the Southern Ocean, the lack of data in the Southern Ocean is definitely a very big problem, right? We need like more data in the Southern Ocean. But like the so-called data, most of the data is measured by the ship, but it's not possible to have like the loss of ship data in the Southern Ocean, especially in winter, right? So I think this autonomous vehicle, like the instrument, like the buoy or like the SUV in the Southern Ocean, should definitely be one of the priority we should do in the future. And also this so-called float data, I think we should have some development of the sensor to make the measurements is more accurate of this float data measurements. Another thing is like I recently working on look at the impact of the bubbles on air-sea gas exchange. So we found like the bubble is very important. It's probably immediate half of the air-sea gas exchange, air-sea CO2 exchange globally. So it's very important. But now we did not we use the Van Hoff parameterization. It should include all the processes, but we didn't separately consider the bubble effect. It's different with the interfacial transfer. So you can imagine the bubble submerged to the system to the upsea water. It's like subjected to the pressure of the water. So the bubble is compressed. So that means the atmosphere concentration is higher in the bubble than in the atmosphere, right? So we didn't account for this effect in the bulk equation. So this is one of the things. So I find like even if there's a very small compression the compression effect, it will be very significant for the global ocean CO2 flux estimates. It's similar with the cool skin effect. This is because globally the PCO2 is very small. It's about -10 micro-ATM. So any process that will make the delta PCO2 change a little bit will be significant globally. So towards this process, I think we should do the measurements in the invasion region. So now we have lots of measurements by eddy covariance in the invasion region, but not in the evasion region. So for this bubble effect, the evasion and the invasion is different. So the bubble will favor the invasion process and make the evasion flux smaller. So I think we need some measurements in the outgassing regions. And another problem is the high wind speed. For this key problem, and I show this figure, you can see like the error bar at the high wind speed is very high. It's very large, the error bar. I think this is related to the bubble effect I just discussed. But maybe there are also some other processes happen. So this is about the K. And about this the PCO2 thing, this temperature correction thing, I still think we need to do that in the open ocean. I previously joined a seminar together with Jim Edison, and he think probably we should do the eddy covariance measurements in the coastal ocean by the tower to get more data. And because that we don't need to do the motion correction, right, based on the tower. So that will make the flux maybe more reliable. But I would argue like in the coastal ocean, which key we should use, because now all the key we have is based on the open ocean. It's not the coastal ocean. But the coastal process is pretty different. But it looks like it's still a key problem. But yeah, so that's what I would just like to say. Maybe in the open ocean, like the wind speed is moderate, not very high, not very low, in the middle. So in the middle, we think the gas transfer velocity is pretty well constrained to have a long time observations, maybe by the buoy or something, to have a long-term observations and use that to confirm, to do something for this temperature correction confirmation. This is just my very shallow understanding. Sorry, I probably can't answer your question, but it's just my understanding.
No, it was just perspective I was looking for, so that's great. Thank you. Thank you. Great. Any further final questions? I don't see any hands. Okay, well, I guess in that case, thank you very much, Yuanxu. I appreciate you taking the time to share this with us, and it is recorded, so it will be put on the SOFLUX YouTube sort of channel to be shared so more people can see it. But for now, thanks very much, and have a great day.
Thank you.
Cool.
Bye-bye.